Okay, now we expand the problem to the number of ways to get 2 5s and 3 face cards of the same denomination. Now the denominations of face cards are jacks, queens, and kings. So that means either we get 3 jacks, that would be 3 of the same denomination, or 3 queens, again, same denomination, or 3 kings. We're not going to mix jacks with kings with queens in these choices. So it's just like getting a full house before, sort of very much similar to the getting 2 5s and 2 9s. But now we're getting 2 5s, and then we'll get 3 face cards of the same denomination. And that's going to expand things just a little bit. Well, it should be clear that there are C of 4 ways to get 2 5s, and there are C of 4 3 ways to get 3 of a given face card denomination. For example, if the given denomination is jacks, there are C of 4 3 ways to get the jacks, 3 jacks. Or C of 4 3 ways to get the 3 queens. The given denomination then would be queens. Or if the given denomination is kings, there are C of 4 3 ways to get those. Okay, well, since there are 3 possible face cards, jacks, kings, and queens, and there's C of 4 3 ways to get 3 of each, there are going to be 3 times C of 4 3 ways to get 3 face cards of the same denomination. Again, C of 4 3 ways to get the 3 jacks, add that to the C of 4 3 ways to get the 3 queens, and add that to the C of 4 3 ways to get the 3 kings, and you have C of 4 3 plus C of 4 3 plus C of 4 3, which is 3 times C of 4 3. So that the number of ways to get the desired hand, that is 2 5s and 3 face cards of the same denomination, is C of 4 2, the number of ways you get the 2 5s, multiplied by 3 times C of 4 3, because there are 3 denominations of face cards. Okay, so that should be fairly clear. Now there's another question, but I'm going to save that for another video because we need a somewhat extensive discussion. Now we have the question of how many ways there are to get a full house unrestricted. Okay, now we can get a full house. We get a full house of let's say 9s and 10s with 2 9s and 3 10s. Or we could get a full house of 3 10s and 2 9s. We could get a full house of 3 kings and 2 jacks, or a full house of 3 jacks and 2 kings. It should be clear that we could pick any 2 denominations in order, because let's agree that the first one we pick will be the one for which we have 2, for which we get 2. Okay, so if we pick 9s and 10s, that means 2 9s and then 3 10s, whereas if we pick 10 9, that means 3 10s and 2 9s, which is a completely different hand. Okay, so it should be clear that for any ordered pair of denominations there is a full house. Now let's think about what we mean again by ordered pairs of denominations. As a matter of fact, I asked people to list all the ordered pairs of denominations they could, and everybody who was in class did pretty well with that. They were able to start listing things, 1 2 1 3 1 4, or maybe 1 2 2 1 1 3 3 1 systematically, and it's clear to me that if I'd have given them time, they would have been able to list all 156 possibilities. Well, let's see how that might be done, though. Let's just look over here. Okay, so here's one way to list them. 1 2 1 3, then some dots for 1 4 1 5 1 6 1 7 1 8 1 9 1 10, and then 1 jack, 1 queen, 1 king. So how many of these are there? Well, we're matching 1 up with any of the other 12, so there are 12 ways to do an ordered pair starting with 1. And then starting with 2, we go 2 1. We can't go 2 2 because we can't pick the same denomination twice. We wouldn't have enough cards. But we go 2 1, and skipping 2 2, we get 2 3, and then we continue on up through 2 king. Clearly, there will be 12 ways we can do that. Then starting with 3, we can list from 3 1 up through 3 king, skipping 3 3. again, 12 ways. And then we continue that until we get down to the kings. We go king 1, king 2, up through king, queen, again, 12 ways. And we're starting with each of the cards, 1, 2, 3, up through king. So there are 13 rows, 12 in each row. So that's 13 rows, 12 in each, and that implies 13 times 12 possible pairs. So that's one way to see that there are 13 times 12 possible pairs. Another way to see it is to attempt to draw a tree. I don't know if I have the camera aimed low enough to see the last of that tree. So we draw a tree. Our first choice will be 1, 2, 3, 4, all the way down through Jack, Queen, King. And I could have numbered these. I have room. There's 5, 6, 7, 8, 9. Looks like I left off 10. I'll squeeze 9 in there and call that one 10. Anyhow, you get the idea. 13 branches here. Then off of each of those branches, we can choose any of the numbers that we don't have here, or any of the denominations we don't have on the first choice. So coming off the first choice, we could choose anything from 2 through king. Now this just corresponds then to the first row, 1 paired with anything from 2 through king. Now I haven't listed it with everyone. If we choose 6 first, then we could pair up the 6 with anything but a 6. So we'd again have 12 branches coming off of the 6. Each choice for the first card gives us 12 possible choices for the second card, 12 branches off of each of these initial branches. And then down to, for the king, we could have anything from 1 through queen. And again, that shows that there are 13 times 12, and that equals 156. And those are ordered choices of 2 denominations. So it should be clear that there are 13 times 12, or 156 different full house hands, different ways to get 3 of one, 2 of the other. Now, we didn't have to do the listing, we didn't have to do this, but it's good to be able to do that, to connect this with our permutations and combinations. What are we doing? We're making an ordered choice of 2 objects from 13, 2 denominations from among our 13. Again, the choice is ordered because it makes a difference whether you do 2 jacks and 3 8s, or 3 8s and 2 jacks, for example. Okay? Well, there's a simple way of expressing that. It's P of 13 2 possible ways. And P of 13 2 equals 13 times 12. And that, of course, equals 156. So we didn't need to do this. We didn't need to do this, although it's good to do this. And it's probably a really good idea to at least think this, imagine it, so that we're sure what we have. But there are P of 13 2 ways to do it, 156 ways to choose the 2 denominations, to choose 1 denomination for 2 cards, 1 denomination for 3 cards. So now over here, having done at least a partial listing in class, we didn't really do the tree, but it's worth imagining the tree as well. The answer to how many ordered pairs of denominations is P is 13 2. There are P of 13 2 ordered choices of 2 from 13. So for each possible choice of the 2 denominations in order, we have C of 4 3 times C of 4 2 times C of 4 3 full houses, possible ways to get the full house. And we multiply that, the CO4 times CO4 ways to get a full house, with a given pair of denominations, given ordered pair of denominations, by the number of ordered pairs of denominations that are available. So we have P of 13 2 times C of 4 2 times C of 4 3 possible full houses.